Logistic regression. Logistic regression is a classification technique, that is, you use the independent variables that you have in order to find a binary outcome. What is a binary outcome? You will have two outcomes, right? Generally, you will call it 0 and 1, or maybe class 1 and class 2. So you'll use the independent variables that you have in order to find which class this input belongs to. Where is it, class 1 or class 2, right? Let us start with the logistic function and let us understand how we use this logistic function in order to identify the right class. When we were previously learning linear regression, we had a function like this. Let us say A is equal to W1x1 plus W2x2 plus W3x3 plus so on. Let's say this is the type of a function we used in linear regression. What were the w's and x's here? A is what we want to find, the value that we wanted to find. W's were the coefficients, w1, w2, w3, etc. These were the coefficients. X1, x2, x3, etc. These were the independent variables that you had. This is how you did in case of linear regression. But keep in mind, there it was not a classification technique. In linear regression, you were trying to find the value of this, the value of A. When you are given any new input x1, x2, x3, using the coefficients w1, w2, w3 that you had, you were trying to find one particular real value for this A. Coming to classification, you don't want to find any real value. You want to find the class to which it belongs. That is, generally you want to find whether this input, let's say x1, x2, x3, this input, whether it belongs to class 1 or class 2, or maybe you will say 0 or 1. In this case, instead of this real value, you want something else. You should be able to classify. That is where the logistic function comes in, okay? And what is the logistic function? Considering this is your value A, logistic function sigma of A is equal to 1 by 1 plus e power minus a. So logistic function is also called as sigmoid function. You call it as sigmoid function because it is an S-shaped function. In the previous lecture, we discussed in detail about what is sigmoid function, how it functions, and why it can be useful in classification tasks. So for details about sigmoid function, please refer the previous lecture. In this lecture, we'll just introduce sigmoid function and we'll see why it is useful in logistic regression. We won't go in deep about this function. So let's start with this. Sigmoid function is 1 by 1 plus e power minus a, where a is this value w1x1 plus w2x2 plus w3x3 up to which point? Up to, let's say there are n values, then wn xn. Okay, this is what a is. So here in logistic regression, you are using this sigmoid function. Why are we using sigmoid function here? Because sigmoid function or the logistic function, it maps any real valued number into the interval 0, 1. That is, it will take a real valued number and it will map into some value between 0 and 1. What is the benefit? Because of it, it makes it suitable for modeling probabilities. Here, when you want to determine class, you want probability. That is, you want the value to be between 0 and 1. During linear regression, you had no such limitations. You wanted to find the real value of the output variable. That is why you did in linear regression. Here in logistic regression, because this is a classification technique, you want probability. And probability should lie between 0 and 1. And this is where the sigmoid function or the logistic function comes into picture, because it has the ability to map any input value to 0, 1, this interval, right? So you can write it like this. Let us say you have two classes, 0 and 1. Then you can find the probability of y is equal to 1 given x as, how do you find it? 1 by 1 plus e power minus a, where a is this value w1x1 plus w2x2 plus w3x3, this value. Okay, so this is what your probability is. Let's say probability of y is equal to 1 is this. What can you infer from this, or how do you find the decision boundary? That is, if you have a lot of points here and you want to decide the classes to which this belongs, you want to find a decision boundary. There should be a decision boundary like this, which would say above this decision boundary it is class C1 and below this decision boundary it is class C2. So how do you identify the decision boundary in logistic regression? This is the first thing you want to know. So let us say you have probability identified like this, probability of y is equal to 1, that is it belonging to class 1. If you identify that probability, you see this value and keep a threshold. Threshold would generally be 0.5. This is your threshold. What is the importance of this threshold? If your predicted value, that is the probability, it is above this threshold or equal to this threshold, then you would say it belongs to class 1. And if it is below that threshold, that is if the probability of class 1 is less than 0.5, then you will say this particular point it belongs to class 2. So this is how you identify the decision boundary. You keep a threshold of 0.5 and whenever the probability is above 0.5, you will say it is class C1. Whenever the probability is below 0.5, you will say it is class C2. So this is the very basic about logistic regression. Let's go deep into this. Let us understand how you find out this decision boundary, what is the mathematics behind it, and once you understand it logically, you would start loving this subject. You would understand all the concepts and you will feel good, right? That's where we are heading to. Let us understand logistic regression in detail. For now, you got a basic overview. Let us get into the mathematics behind. Okay, so I'm rubbing this off. Keep this in mind, the sigmoid function. This is very important for this lecture. So A, I hope you'll remember this value of A. I'm just removing this as well. This is your sigmoid function. So I'll just rewrite the sigmoid function and start. Just let us say sigma of A. Just remember this is the sigmoid function. Okay. So we just discussed about probability of y is equal to 1 given x, for which we wrote it as 1 by 1 plus e power minus a, where a is w1x1 plus w2x2 plus w3x3 plus up to wnxn. Okay, that is your a. So the next thing that you have to understand is how you can generalize this. That is, instead of writing this as p of y equal to 1 given x is this and p of y equal to 0 given x is something else, how can you generalize this? That is the same thing. What will be p of y equal to 0 given x? What will be p of y equal to 0 given x? Can you say from this? Because you know there are only two classes, 0 and 1. You know this is the probability that y equal to 1. Given the value of x, this is the probability that y equal to 1. You have only two probabilities. Then what can be the probability that y equal to 0? It will be 1 minus probability of y equal to 1 given x, right? So that is 1 minus sigma of a, sigmoid function of a. This is how you can write probability of y equal to 0. How can you now generalize this and write it in a single equation? How do you generalize these two things? This can be generalized as probability of y is equal to, let's say y given x is equal to, how can you write this? Sigmoid of a to the power y into 1 minus sigmoid of a to the power 1 minus y. How does this make sense? Just see substituting. Substitute the value of 0 to y. If you substitute 0, this term will go off, this term will stay, right? Because this will be raised to 0, which will be 1. So this will go off and this term will stay because 1 minus 0 will be 1. So it will be 1 minus sigma of a, which will be this one. What if you choose the value of 1 to y? In that case, this will stay and the second term will go off because here 1 minus 1 will be 0. So this term will go off. If this goes off, sigma of a only stays, which is this one, p of y equal to 1. So this is how you can generalize the above two equations by writing p of y equal to y given x is equal to sigma of a to the sigmoid of a to the power y into 1 minus sigmoid of a to the power 1 minus y. This is how we generalized. So we are going step by step. Now that we generalized, what is the next step? How do you identify? See, the whole point here is to identify the values of W. That is what you derive in all these machine learning techniques, be it linear regression, logistic regression, whatever. what do you want to find W's? Because if you know the W, from W you can find, you already know the value of X, which is the input. So if you know the W, you can find W1 X1 plus W2 X2 plus up to Wn Xn, right? This value you can find because Xn is your X is your input, X1, X2, X3, all these are there in your input. W's are your coefficients. Once you know W, you can easily write the sigmoid function. Sigmoid function is 1 by 1 plus e power minus a. So once you know the value of W, you can easily find the value of sigmoid function. And if this function turns out to be greater than 0.5, then you can say it is class 1. If it is less than 0.5, you can say it is class 2. It's as simple as that. So the only task here is how do you identify the value of W? That is what this whole derivation is about. Okay. So the next task is to identify W. How do you identify W? You have this function here, which will tell you what is the probability of it belonging to each class. Okay. The next thing is to find the likelihood. So why do you want to find the likelihood? Because likelihood would tell you the probability of the observed data given a set of parameters in the model. That is, if you set these parameters, let us say you fix these parameters to some value, W1, W2, all these, you fixed it to some value. Then your likelihood will tell you what is the probability of observing one particular data. So what you have to do is you have to find the W's which will maximize the likelihood. That is the whole task. So if you find the value of W's, the coefficients, which will maximize the likelihood, that is the perfect value of W that you want. Let us see what is the value of likelihood and how we can maximize it. Okay. So we are going to find W's. Likelihood. Likelihood can be written as likelihood of the coefficient is equal to. So previously we talked about this formula, but keep in mind that this is when you just have one data point. For one particular data point, whether it belongs to class 0 or class 1. That is what this formula identifies. But what if you have m different data points? You will have a lot of input, right? And you have to identify all those. So instead of one data point, when you have m different data points, what will be your likelihood? So this probability, this can be written as, when you have m different input, what will you do with the probabilities? You will multiply all those probabilities. So it will be multiplication of I is equal to 1 to m, right? What is the value? Probability of yi given xi and w. Okay, you are given the value of w, you have an input xi, then what is the probability of yi? So you will be multiplying all the probabilities. That is, here you have the probability for one particular point, and in case of likelihood, you are taking m different inputs that you have and you're multiplying the probabilities of all those points. Likelihood of all those points you're multiplying in order to find the total likelihood. And your task is to maximize this likelihood, right? So let me start simplifying this. This can be written as, taking it from this equation, I'll write it as pi I is equal to 1 to m. Probability of yi given xi can be written as sigmoid of ai to the power yi into 1 minus sigmoid of ai to the power 1 minus yi. Okay, so I just used this equation in order to rewrite this to here. Okay, it is clear? I'm going to rub this off. Okay, so I use this equation in order to write the above one. So now we know this is the likelihood. Some product of I equal to 1 to m different points, sigmoid of ai to the power yi into 1 minus sigmoid of ai to the power 1 minus yi. This is your likelihood. The next task is how can you maximize this likelihood? So the first thing I'll do for that is take the log of likelihood. Why am I taking log? Because this is a complex equation. That is, if you want to take the derivative, find the extremes, this can go complex. So in order to simplify it, taking log always helps. So that is where we'll take log and then find the maximum likelihood, because taking the likelihood and finding the maximum, or taking the log of likelihood and then finding the maximum, both will give you the same final effect. So we are going to take the log. So log of likelihood, I'll call it L of W. So this is log likelihood. I'm taking log of this value. Okay. So when I take log of this, what will happen? This product will turn to summation. That's what happens when you take log. Okay. So I'll just write it like this first. Log pi I is equal to 1 to m sigmoid of ai to the power yi into 1 minus sigmoid of ai to the power 1 minus yi. If I'm taking this log, then what happens? The summation product will become summation. So it will be summation I is equal to 1 to m. Inside that, what will this term become? I'm taking log. So again, this product will also become summation. So it will be log of sigmoid of ai to the power yi plus log of 1 minus sigmoid of ai to the power 1 minus yi. So this is the log likelihood. How can you simplify this? If I take this is of the form log a raised to b. Log a raised to b is same as b into log a. So instead of log of sigmoid of ai to the power yi, I can write it as, I can take this yi here. So it will become yi log sigmoid of ai. Similarly, if I take this 1 minus yi to the left hand side, this will become 1 minus yi will come here. So it will be 1 minus yi into log of 1 minus sigmoid of ai. So this is my log likelihood now. Okay. So I'll erase this off. So now you got the log likelihood. What is the next thing? You want to maximize this log likelihood. So first thing, we took log just to make the computation simple, and now you have to maximize this. But generally, with the cost function, what do you generally do? You minimize the cost function. You generally don't maximize. So in order to take it to that general narrative of minimizing the cost function, just for that purpose, instead of this log likelihood, we will take negative of log likelihood. That is, maximizing this value is same as minimizing negative of the same value. So for that reason, we will take negative of log likelihood. So I'll call it J of W. This is negative of log likelihood. Okay. So what will this be? This will be minus. I'm just putting a minus and copying this whole thing. Okay. Because it's log likelihoods negative. Sigma I is equal to 1 to m yi log sigma of ai plus 1 minus yi log 1 minus sigma of ai. Okay. So this is my negative of log likelihood. So what do I have to do now? Now I have to minimize this, because log likelihood I had to maximize, but negative of log likelihood I have to minimize. It is minus of sigma I equal to 1 to m yi into log sigma ai plus 1 minus yi. Let me correct this. 1 minus yi log 1 minus sigma ai. Okay. Ai is not clear again. This is ai. Okay. 1 minus sigma ai. So this is my negative log likelihood. What do I have to do? What do I have to do now? I have to minimize the value of negative log likelihood. That is the next task. Okay. So in order to find, just before minimizing, I'll do one more thing. That is, this is the total cost that we are calculating. So to find the average cost per example, that is, here we are having m different examples, right? M different examples. So in order to find the average cost per example, I'll divide this by m. So it will be J of W, modified J of W will be 1 by m into So that minus sign I'll put here. Sigma I is equal to 1 to m yi log sigma of ai plus 1 minus yi log 1 minus sigma ai. Okay, so this is what I am going to minimize. I'll erase this off. Now you know what you have to minimize. The next step is minimizing this cost function. So whenever you minimize this cost function, you will find the best fitting model parameters, the WIs. So WIs are what you want to find, right? That is our aim. So now we have to minimize this. How you have to minimize? You have to minimize with respect to WI. That is, each WI, for each of the WI, you have to minimize and find its value. That is, you had W1, W2, W3, etc. What you have to do here is, you have to minimize this function J of W, negative of log likelihood, with respect to each of these Ws. Each of these Ws, with respect to each of those, you have to separately minimize them and find the optimal value of W1, W2, W3, etc. Okay, let us generalize it as Wi and find the do the mathematics. Okay, so if you want to minimize, what you have to do, del by del Wi of J of W. This is what you have to do. Del by del Wi of J of W. How will it look like? Del by del Wj of J of W. You have to take derivative of this whole equation. So wherever Wj is applicable, that is where you apply the derivative. So this will be minus 1 by m into summation I is equal to 1 to m yi. So why am I not applying derivative to this yi? Because there is no wi term in yi. So there is nothing to take derivative of. Del by del wi of log sigma ai plus 1 minus yi, 1 minus yi into del by del wi. Let me, okay, this I and the other I is coinciding, right? Let's call this Wj, because otherwise you will have confusion with yi. Okay, so I'll call this Wj. All the W's I'll change to Wj. Del by del Wj of log 1 minus sigma ai. Okay, so this is what you want to find now. So in order to take this derivative, what are the terms that you have to learn about? One is this term, which is del by del Wj of log sigma ai, and the other term is del by del Wj of log 1 minus sigma ai. If you know both these terms, the remaining you can find out. Okay, so let us find both these terms now. First term is this one, del by del Wj of log ai. So in order to make that simpler, let me first find what is del by del ai of sigma ai. That is, if you have logistic function, what is the, simply if you take a logistic function, what is the derivative of that logistic function? So we already discussed this in the logistic function lecture, that is the sigmoid function lecture. What is the derivative of the sigmoid function? It is sigmoid of ai into 1 minus sigmoid of ai. So it is a derivative based on the same function. This is the beauty of the sigmoid function. So let us find the derivative of this term, del by del Wj of log sigma ai. So del by del Wj of log sigmoid of ai. What is this value? This value is, if you want to, when you take the derivative of log, what will it become? It will give, log x will become 1 by x, right? So 1 by sigma ai, that is the derivative of log part. Now we have to take the derivative of sigma of ai. What is the derivative of sigma of ai? You can see from here. So I'll write sigma ai into 1 minus sigma ai. Okay, this is fine. The next thing is, what is the derivative of ai? You are taking with respect to Wj. So there is only one x term which corresponds to wj, which is xj. So it will be xji. So this will be the derivative del by del wj of log sigma ai. So it will be, so here this will both cut off. So what remains is 1 minus sigma ai into xji. Okay. This is what remains. So I'll write it on top. Del by del wj log sigma ai can be found as 1 minus sigma ai into xj of I. Okay, xji. This is what is this term. Del by del wj of log sigma ai can be written as 1 minus sigma ai, 1 minus sigma ai into xji. Okay, xji. The next term is this one, 1 minus del by wj of log 1 minus sigmoid of ai. So del by del wj log of 1 minus sigma ai. How can you find this term? The same way you did for the previous one. What is the log of log x? Derivative will be 1 by x. So it will become 1 by 1 minus sigma ai. Okay. So next thing is 1 minus sigma ai will become minus of the derivative of sigma ai. So it will be minus, I'll put that minus here, into sigma ai into 1 minus sigma ai. What is this? This is the derivative of sigmoid function. Sigmoid of ai into 1 minus sigmoid of ai. And next, derivative of ai with respect to wj. What is the derivative of ai with respect to wj? There is only one x term, so it will be xji. That is only one x term corresponding to that particular wj, that is xji. Okay. So here this will both get cut off. So what remains is minus sigma ai into xji. So I'll write it neatly. What remains is minus sigma of ai into xji. This is what remains. Okay. So now you know the derivative of first and second term that you wanted. This is the first term. This is the second term. You know the derivative of both. Now what can you do? You can substitute that. That is, instead of here del by del wj of log sigma ai, you can substitute this value. If I substitute that here, it will become 1 minus sigma ai into xji. Okay. And what will be the derivative of this term? Del by del wj of log 1 minus sigma ai. I can substitute this value. If I substitute that, this will become minus sigma of ai. So that minus I'll put here, minus sigma ai xji. Okay. So this is the derivative. This is the derivative with respect to wj. Can I simplify this? Yes, I can. How can I simplify this further? If I simplify this, this will be, I can take xji common out from all these. So it will become minus 1 by m into sigma I is equal to 1 to m. I'm going to take xji common out of everything. Okay. So it will be xji into, what will the first term become? It will be yi minus, second term will be yi into sigma ai, right? Yi into sigma ai. Then this term, this will become plus sigma ai. And the last term will be plus yi sigma ai, plus yi sigma ai. So here this minus yi sigma ai and plus yi sigma ai, this will get cancelled. So this is gone and minus yi sigma ai is gone. So what remains is this. Okay. Minus of xij into yi minus sigma ij. So this will be yi minus sigma ai. So this will be yi minus sigma ai. Now I am going to take this minus inside. That here you can see a minus. This minus I am going to take inside. So if I remove this off, this will become the other way around. This will be sigma ai minus yi. Okay. So this can be written as xi into sigma ai minus yi, right? So this is your final derivative. If you take the derivative with respect to wj, this is what you finally get. Okay, so it is del by del wj of j of w. What is j of w? It is the negative of log likelihood. If you try to minimize it with respect to wj, you will get this term 1 by m into sigma I equal to 1 to m xji into sigma ai minus yi. So this is the final derivative that you get. What is the next step? You found the derivative. So what are we working towards? We are working towards finding the value of w's, the coefficients. Okay. So here you found the derivative. The next step is gradient descent. So what is gradient descent? Gradient descent is the method by which you step by step get towards the best value of w, the optimal value of w. That is, you initially fix some random value for w. In the from previous lectures, you would already be knowing this. You will take a initial value w0, let's say. For initial value, w0 will be confusing. For each of the wj's, you will take some initial value, let's say 0 or maybe some very small value. What will you do from there? You will try to find the optimal value of wj by updating the value of wj in each iteration. So in each iteration, you will take this negative log likelihood, you will minimize it with respect to w. So you know what is this is called as gradient, the derivative with respect to wj, this is called the gradient. Using this gradient, you will update the value of wj here. Okay, how will you update? Your new wj, which is wj plus 1, that is after the updation wj plus 1, that will be wj minus eta into del by del wj of j of w. So this value is here, del by del wj of j of w, that is this value. This you have to use here. This gradient you have to use and find the value of wj plus 1. That is in order to update w. Here it's better I write wj itself, because wj plus 1 will mean the next coefficient. What I mean to say is wj but the updated wj. Okay, it's not wj plus 1, it is wj updated. Okay, wj dash maybe. So wj dash, it is wj minus eta. Eta is the learning rate. In the previous lectures we had seen learning rate. It will determine at what speed you want to learn. Okay, you have to find the optimal learning rate. If you keep it very fast, it may not converge. Okay, so learning rate into gradient, and in place of gradient I can substitute this value. Okay, so if I substitute this, then this will become wj minus eta into 1 by m sigma I is equal to 1 to m xji into sigma ai minus yi. Okay, so this is your gradient descent formula. So what do you have to do with this gradient descent formula? This formula you have to apply it iteratively to adjust your wj's, and you'll be adjusting it in the direction that reduces the cost function. And what will ultimately be the result? It will ultimately lead to the best fitting logistic regression model. So model in the sense, the value of w. If you know the value of w, you know the perfect fitting model. Finding the coefficient is what the whole topic is about. So using this gradient descent, when you do iteratively, next iteration, in each iteration, your w will come towards the best version of w. And how do you decide that this is the best version? It is converged. I should stop iterating. How do you decide that? In order to decide that, Most common technique that is used is you will keep a threshold, that is your wj dash minus wj. This value, this norm, you will say if it becomes less than some threshold, if it becomes less than some threshold value, then you would say it has converged. So this threshold you will keep very small, generally something like 0.001 or something like that. So this depends from case to case. In some cases 0.01 may be the right value, in some cases 0.0001 may be the right value. That you have to identify. So you will find the updated W and the previous W. The difference between them is so small that it is lesser than the threshold you have set. Then you would say it has converged. This is one way of saying you found the perfect value of W. The other value is if the gradient is close to 0. That is this gradient value that you are finding. If this value is very close to 0, if it is very close to 0, then there is no point in updating, because if this value is very close to 0, this whole thing will be 0. So there will be no point in updating. Then also you will say, okay, it is converged. And the third thing is, you will keep a number of maximum iterations. Let us say you are saying, I want to iterate for a maximum of 1000 times. This is the ultimate maximum. If it has already done 1000 iterations, then you will declare that it is done. You will say this is completed, this is already converged, this is the best value of wj. So you are doing this in order to avoid infinite loop. That is, if it keeps looking for better and better w's, and if it is not reaching this threshold, in order to avoid that situation, you will keep a maximum number of iterations. So these are the generally these are the methods that are used. One is to see if it is less than a threshold. Second thing is to see if gradient is approaching 0. And the third one is to keep a maximum iteration number. So if it crosses that iteration number, you will say it has converged. Whenever it converges, at this point, you know the value of all the wj's. When you know the value of wj, using this, you can find the value of logistic function. And if that value is larger than 0.5, you can say it is class 1. If it is less than 0.5, you can say it is class 2. This is how logistic regression works.